Hello everyone, today I would like to introduce my work, Design of a Real-Time Human-Robotic Collaboration System using Dynamic Gestures. I'm the presenter Haodong Chen from Missouri University of Science and Technology. My advisor is Dr. Ming Lu. This is the outline. The main tasks include algorithm and interface design, also human-robotic collaboration system construction. The experimental results show the feasibility of the whole system. Currently, in the view of the flexible automation in industry, human-robotic collaboration systems become one of the promising solutions. However, in the application of the human-robotic collaboration, space separation and time separation of human workers and robots result in low productivity. To improve this situation, different communication channels were used, including the gesture, verbal, EMG, and EEG signals. In all these communication channels, the gesture is more desirable for the human-robotic collaboration system because in a manufacturing task, the keyboard is not always easy to use, and the verbal will be affected by the background noise. The EMG and EEG signals are not straightforward as a gesture to be understood. So in this paper, we choose the gesture as a communication channel between the human worker and the robotic arm. This is the system overview. A RGB camera was used to collect the current movements. A multi-threading model was constructed to realize the execution of multitasks. The first one is the software interface. The second one can generate the real-time motion history image. The third one uses a pre-trained deep learning model to recognize the current gesture. The last one can transmit the final results into the software interface and the robotic arm. Then the robotic arm can perform corresponding movements. In the previous work, we designed a set of dynamic gestures, used the video-based motion history image to extract gesture features, constructed a deep learning model for dynamic gesture recognition. The accuracy was higher than 99%. In the previous work, the video-based motion history image method was used to extract the features of a dynamic gesture video. It is a scalar-valued image, where the more recently pixels are brighter and vice versa. But the video-based motion history image method cannot work well in a real-time situation because it cannot detect accurate start and end time of a gesture. Also, for different gesture of different human workers, the duration time is different and varies. To eliminate the elimination of the video-based motion history image, in this paper we improved it and designed the real-time motion history image method. Note that all the frame rate in this paper is 30 frames per second. First, we changed the time difference to 1, which means that each new input frame I, X, Y, T can generate a new binary image and a new motion history image, like this video shown. And next, we can say all the input white pixels will change to black after a while, so we need to define the duration time tau of these white pixels on the motion history image. Based on our dataset, the duration time was set as 35 frames. In all pictures, the picture value is changed from 0 black to 255 white color, which means that, like in this video shows, for each new input white pixels, it will change from 255 to 0 after 35 times decay. So the decay parameter can be calculated using 255 over 35. The result is 7.29. And we can use this as a final function to generate the real-time motion history image. This is the decay parameter, dirt. This is the pseudocode of the real-time motion history image generation. This is the software designed for the system operation and visualization, including 2 buttons, 2 windows, probability distribution label, and the recognition label. And this is a real-time motion history image. In this paper, we constructed a multi-threading model to realize the 4 different parallel tasks can be conducted at the same time. And here we can see the software thread, MHI thread, recognition thread, and transmission thread. Here, a lot of different variables were transmitted between all these different threads in a real-time way. This is the software interface thread to show the real-time motion history image and current frame, also including the system operation buttons. These are other 3 threads. It can be seen that the real-time motion history image will be transmitted into the software interface and also recognized by the 3rd thread. The final recognition label can be transmitted by the 4th thread into the software interface. Based on pre-trained deep learning model for gesture recognition, we applied more augmentation method for the data augmentation, including brightness change, shift, scale change, and perspective change. The softmax function was used to calculate the probability of the final results, which can also be seen as a similarity between the final results and all the gestures. In the system experiments, a 6th degree of freedom E.Do robotic arm was used, and the end effector is a gripper. This table shows the information of all these 6 joints. The designed 10 gestures can be divided into calibration gestures and operation gestures. The calibration gestures can instruct the robot to do some routine procedures, such as the start and the stop. The operation gestures can instruct the robot to move the end effector along 6 directions of the workspace or control the gripper to open or close. This video shows the real-time motion history image. These are some hardware and software information of the whole HRC system. The RGB camera in this system is the Logitech HD webcams camera. This is the real-time motion history image and the real-time recognition of the gesture right. It can be seen this gesture was recognized correctly with a higher probability. And when the robotic arm obtained the final result, it would move the end effector to the right, no matter which position it was, and it can be seen here. In order to satisfy the safety, the moving distance for each input gesture is set as 5 centimeters. This is another example for the gesture outward. It can be seen the gesture was recognized correctly, and these are the robotic movements for the input gesture outward. These are the recognition results of invalid gesture, including the movements out of designed gestures and no input movements. Also, in the video of the real-time gesture recognition, it can be seen the recognition of the invalid gesture here. In this paper, a brand new human-robotic collaboration system was designed using the deep learning model. A multi-threading model was designed for this system. An improved real-time motion history image was proposed. The system was integrated with the dynamic gesture deep learning model and the robotic arm. This work is supported by the National Science Foundation and Missouri University of Science and Technology. Thanks for your listening. If you have any question, you can ask me or email me.